Okay, so now that we've talked about computing the little deltas, and we have those already done for all the neurons in the network, let's talk about computing the actual deltas and all of the weights. Let's say, for example, that we have a little tiny network that looks like this. I'll call this first layer J, I'll call this second layer K. Let's just use this as a perfect example and it'll generalize obviously. So since layer J has 3 neurons, 2 actual neurons and a bias neuron, and layer K has 2, the weight matrix W is 2 by 3 and looks like this, right? I have the weight from 1 to 1, the weight from 2 to 1, the weight from 3 to 1. Those all link to this first neuron. Those would all be multiplied by the column vector, which is these values right here to get all of this input over here. So, et cetera, et cetera, et cetera. So let's say I do know, if we can recall this, I do know how to do it individually, right? If I have a delta for this layer and I multiply it by the output of a node in the previous layer, then that is the change in the weight that connects the two. I mean, you have to include the learning rate and all that junk, but essentially that's it. So let's just write down let's pick one and do an example. So let's say we pick the first node of layer J and the second node of layer K. Then the change in that weight from 1 to 2, which is this guy right here, is going to be the output of the first node in layer J times the delta of the second node in layer K, which right here you can see is script O sub 1 upper J times little delta sub 2 upper K. All right? So in order to figure out how this matrix should look, let me just write down what all of these elements should be because it's easier to do them individually. Well, let's see, the change in the weight from 1 to 2 is output of 1 times delta of 2. So that's output of 1 times delta of 2. Let's see, the change in weight from 3 to 1, so that's from the bias node to this first neuron, is going to be the output of 3 times delta 1, which is this upper right-hand entry. Now, I guess the step we need to do right now is say, okay, I have this matrix. I want to write this down as a matrix product of stuff that I already know. How do I do that? Well, just like this. This is the step I think is the least obvious, but it's not hard once you see it. So it is the product of the column vector of deltas, which I have right here. I have 2 of them, delta 1, delta 2, and the row vector of outputs, output 1, output 2, and output 3, even though really output 3 is a 1. That's irrelevant in this example. And this produces the same matrix. So this is a 2 by 1 matrix. This is a 1 by 3 matrix. So the result is 2 by 3. And let's pick some entries. So first row times first column is output 1 times delta 1. Second row, third column is going to be delta 2 times output of 3. Boom, boom. And that's it. This column vector of deltas I already have. This row vector of outputs I better already have. I've run the network forward. And so you take their product and that's it. So the thing that I was alluding to earlier is in the actual implementation details, which I won't talk about here because it's not part of the development of the algorithm, but I'll mention it, is that when we run multiple training cases through, this single column vector of deltas will in fact be many columns. And this list of outputs will be many rows because we'll have one set for each different set of inputs that correspond to one of these columns of outputs, which are these deltas here, sorry. So this, actually computing this for each one of those, when this ends up being a big matrix and this ends up being a big matrix, is just a little bit tricky, but it's just an implementation detail, and we'll talk about it if you watch that video on doing all of this in Python. So I hope that was helpful and makes sense. Let me know if you guys have any questions. You can drop them down in the comments, and hopefully I can get back to you, and hopefully I know something about it. So anyway, see you guys later.